अस्सलाम सेशन को जी हम स्टार्ट करेंगे। कल लास्ट लेक्चर में हमने एक छोटा सा एक रिविजन से यहाँ बताता हूँ। हमने यहाँ तक इंडिविजुअल जो स्ट्रेसेस थी उनको डिस्कस किया विद सर्टेन एग्जांपल्स, जिसमें एक्सियल जो स्ट्रेसेस थी, एक्सियल नॉर्मल स्ट्रेसेस, जिनको हमने डिस्कस किया और हमने पिछले कुछ लेक्चर्स के अंदर ट्रस्ट का एक न्यूमेरिकल था उसको सॉल्व किया। देन वी मूव टुवर्ड्स बेंडिंग स्ट्रेसेस। हमने कहा कि बॉडीज़ के ऊपर जब ट्रांसवर्स लोडिंग लगती है देन दे आर सब्जेक्टेड टू दीज बेंडिंग ऑफ फ्लेक्सुरल स्ट्रेसेस सिग्मा इक्वल टू एम बाय ओवर आई। मैं इसके साथ वन नोट भी ऑन करता हूँ ताकि मैं चीज़ें साथ साथ दिखाता जाऊँ। उस फ्लेक्सुरल स्ट्रेसेस को भी काफ़ी डिटेल के साथ हमने डिस्कस किया बीम्स के ऊपर। देन देयर वाज नॉर्मल स्ट्रेस के बाद शीयर स्ट्रेस आई। शीयर स्ट्रेस के अंदर फर्दर 3 टाइप्स थी। एक एवरेज शीयर स्ट्रेस जिसका हमने एक पिन वाला न्यूमेरिकल किया था कि एक सपोर्ट थी जिसके एंड के ऊपर एक पिन दी हुई थी और बेसिकली दैट वाज सब्जेक्टेड टू अ डबल शीयर। और उसके एंड पे मैंने एक असाइनमेंट दिया आपको कि उसी न्यूमेरिकल को सॉल्व करना है, कंसीडरिंग दैट द पिन इज नाउ अ सिंगल शीयर subjected to single shear, then find the diameter of the bolt which is required to resist the applied loading. Then we discuss about transverse shear stresses, which has a different formula VQIT, and we discuss the variables like what V stands for, what is Q, I and T. तो हमने हर इस इन डिफरेंट सिनेरियोज की जो ये डिफरेंट टाइप्स थे इंडिविजुअल स्ट्रेसेस की, इनके वेरिएबल्स को भी डिस्कस किया और साथ इनकी एग्जांपल्स भी की. Then the last was a torsional shear stresses. We also denoted by tau, and the formula is Tc over J. We discussed that in real life the bodies are not subjected to individual stresses. However, they are being subjected to different kinds of loading simultaneously. As a result, if the bodies are subjected simultaneously with different kind of loadings, so they will result in different kind of stress being generated in them. So instead कि अब आप individual stresses को देखें, body के अंदर different kinds of stresses simultaneously occur कर रही होंगी. So you have to check their combined response. ये combined stress देखनी पड़ेगी. ठीक है, maybe there is a possibility that due to applied loading, applied loading ऐसी थी जिसकी वजह से body के अंदर maybe axial stresses भी develop हुए, and the body is also having transverse shear stresses. There may be a case कि body के अंदर bending flexural stresses भी develop हुई हैं और साथ उसके अंदर average shear stress और transverse shear stress develop हुई हैं. So you need to combine these stresses. So we discuss कि एक तो इन सारी individual stresses के intensities या इनकी जो amount है, this is important that you should be able to calculate the value of MC over I accurately. ठीक है, आपको पता होना चाहिए what is the value of internal force, what is C, what is I. That is why we discuss each of these variables. Addition to this, when we come towards the concept of combined stress, ठीक है, तो वहाँ पर इन वेरिएबल्स या इन क्वांटिटीज को कैलकुलेट करने के साथ साथ द नेक्स्ट इम्पॉर्टेंट थिंग इज टू फाइंड द एक्यूरेट साइन ऑफ दीज क्वांटिटीज. मैं एनोटेट करता हूँ. वी डिस्कस कि जिस तरह ये फॉर्मूला है, दिस फॉर्मूला इज बेसिकली इक्वल टू प्लस माइनस एफ ओवर ए. ठीक है, similarly this bending flexural stress sigma equal to mc over I. You also have this one plus minus my over I or mc over I, whatever it is, no problem. So each of these quantities may have a positive sign or it can have a negative sign. ठीक है, so while discussing individual stresses, जब हम इस केस को डिस्कस कर रहे थे अलग-अलग इन सारे केसेस को, so I told you why when you have to consider a positive sign and when you have to consider a negative sign. ठीक है, the reason being why the sign is important because let's say कि आपके पास दो केसेस थे, यानी आप अप्लाइड लोडिंग की वजह से बॉडी के अंदर एक फ्लेक्सुरल स्ट्रेसेस डेवलप हो रही हैं और बॉडी के अंदर अप्लाइड लोडिंग की वजह से ट्रांसवर्स शीयर स्ट्रेसेस भी डेवलप हो रही हैं. जस्ट इमेजिन लाइक द मैग्नीट्यूड ऑफ दिस फोर्स वाज 10 एंड इसका मैग्नीट्यूड लेट्स से 5 था. ठीक है, नाउ इफ you have to find the combined state of stress, so the combined state of stress would be equal to that the sum of these two quantities. So either you can add 10 plus 10 plus 5, or maybe you can add minus 10 minus 5, or you can say plus 10 minus 5, or you can say minus 10 plus 5. All these quantities have different answer, so which one you have to choose? So one of them is correct because you need to have correct senses. आपको पता होना चाहिए कि ये जो दो quantities आपने निकाली थी, the first flexural stresses और the torsional transverse shear stresses, उनकी quantities तो same है in all of these cases, मगर sign different है. सो वो स्टूडेंट जिनको करेक्ट सेंस डेवलप करना आएगी या जिनके कॉन्सेप्ट डेवलप होंगे, जिस तरह हमने लास्ट लेक्चर के अंदर काफ़ी डिटेल के साथ मैं आपको दिखाता हूँ, लास्ट लेक्चर में हमने इस तरह हम डिफरेंट केसेस भी जो है वो डिस्कस किए थे और एग्जांपल्स के साथ मैंने बताया कि व्हेन यू हैव टू कंसीडर अ पॉजिटिव एंड व्हेन यू हैव टू कंसीडर अ नेगेटिव साइन. ठीक है, अच्छा. अब आगे मूव ऑन करते हैं हम. Next slide is the concept of brittle versus ductile material. ठीक है जी. We have two different kind of categories for material. It's very basic thing. आपने physics में पढ़ा. Brittle materials are that they fail at once without giving any warnings. Ductile materials are the one that undergo deformation first before failure. Like they go under large deformations before failure. Ductile इस वजह से होते हैं. तो उसने यहाँ पर एक sentence लिखा है that brittle materials less resistance to normal stresses. Normal stresses कौन सी थी? These one. ठीक है. और दूसरी वो बता रहा है, कहता है कि ductile materials they have less resistance to shear stresses. ठीक है, ये just MCQs हैं आपके समझने के लिए. First you must know that brittle और ductile में फर्क क्या है, and then brittle material हमेशा less resistance होते हैं towards normal stresses, और जो ductile होते हैं they are less resistant towards shear stresses. Don't worry about these things. Stress elements later on we will discuss in detail कि ये हो क्या रहा है. Basically this is a concept which is called stress transformation. हमने until now stress elements को discuss किया था. ठीक है, like this is a stress element. What is a stress element? Like I'm just give few seconds here. For example, हमने ये discuss किया था कि like if this is a body, so the body is composed of several stress elements. You can say it. इसमें बहुत ज़्यादा stress elements है. ठीक है जी. अगर आपको किसी भी पॉइंट के ऊपर लेट से कहा जाता है कि जी ये एक बीम है एंड फ्रॉम द हिंज सपोर्ट, लेट से दिस इज अ हिंज सपोर्ट, दिस इज द रोलर सपोर्ट. इफ यू आर बीइंग आस्क्ड दैट फाइंड द स्टेट ऑफ स्ट्रेस in this beam, like 6 feet from hinge support and 2 inches from top surface. It means top surface से 2 इंच नीचे आना है इस जगह पे. अब आपको इस जगह के ऊपर स्टेट ऑफ स्ट्रेस मालूम करनी है. सो फर्स्ट यू विल डू कि हिंज सपोर्ट से 6 फुट के ऊपर आप एक सेक्शन कट करेंगे. ठीक है, व्हेन यू कट अ सेक्शन, ठीक है, बट इस सेक्शन के ऊपर डिफरेंट एलिमेंट्स हैं. यहाँ पे भी एलिमेंट है, यहाँ पे भी एलिमेंट है, यहाँ पे भी एलिमेंट्स है, किसी जगह पे भी हो सकता है along the depth. But you are asked to find the state of stress 2 inches from top surface. It means this is the point यहाँ पर आपको find करना है, which is 2 inches below. Okay, so you will identify, you will actually place or you will take a stress element from this point. यहाँ से एक stress element लेंगे और इसको analyze करेंगे कि इसके ऊपर state of stress क्या है. So this is basically kind of a sampler. ठीक है, ये kind of body का sampler है. Sampler. जिस तरह आप लेट्स से बीमार होते हैं, कुछ भी हुआ, डॉक्टर के पास जाते हैं, डॉक्टर आपको कहता है कि जी बिफोर आई जस्ट डायग्नोज कि आपको प्रॉब्लम क्या है या मैं उसको क्योर किस तरह करूँगा, ही विल सजेस्ट कि ओके जस्ट गो थ्रू दीज टेस्ट. आपका टेस्ट कंडक्ट करेगा और देन ही विल सजेस्ट कि हाँ ये प्रॉब्लम है और ये इसकी दवाई है. तो जब आप टेस्ट कंडक्ट करने जाते हैं, दे विल टेक सम ब्लड फ्रॉम योर बॉडी. ठीक है, सो उस ये नहीं होता कि आपकी पूरी बॉडी को उसने निकाली, उन्होंने उसमें से एक छोटा सा एक सैंपल निकाला है ब्लड का. ठीक है, और दे परफॉर्म टेस्ट not on your complete body, but they perform those tests on those samples, ठीक है, जो blood samples लेते हैं. In the same way, if you are being asked to analyze the beam for a particular location, so you will take a sampler from that point. That sampler is basically a stress element, ठीक है. तो लेटर ऑन हमने इस पे ये भी डिस्कशन की थी दैट दिस हैव बीन शोन विद दीज साइंस लाइक दिस वन, एंड दीज आर द नॉर्मल स्ट्रेसेस. इन एरोस को हम नॉर्मल स्ट्रेसेस कहते हैं. वी कॉल देम एज नॉर्मल स्ट्रेसेस लाइक सिग्मा एक्स, call them as sigma x, call them as sigma y. Similarly, we also have like these things which we call as shear stresses, tau xy, tau xy. And we discuss about this thing head to head and tail to tail load, how you can actually orient these heads and tails of these shear stress symbols. ठीक है. चलिए वापस शेयर स्क्रीन में आते हैं. एक मिनट, शेयर स्क्रीन. अच्छा, तो इस स्ट्रेस एलिमेंट को बेसिकली उसने यहाँ पर शो किया हुआ है, एंड लेटर ऑन इट इज शोइंग कि वंस द स्ट्रेस एलिमेंट इज बीइंग ट्रांसफॉर्म, इसको ट्रांसफॉर्म किया है तो उसकी वैल्यूज चेंज कर गई हैं. अब ट्रांसफॉर्म स्टेट ऑफ स्ट्रेस क्या चीज़ है, या स्ट्रेस ट्रांसफॉर्मेशन क्या है, वी विल डिस्कस इट इन डिटेल. हम लेटर इसको बड़ी डिटेल के साथ डिस्कस करेंगे in next few slides, but I will just give you some idea here. For example, this is a beam and unloaded stage के अंदर के अभी इसके ऊपर कोई लोड नहीं लगा. This is an unloaded stage of beam. So if you take the sample would be like this one. ठीक है, ये इसकी undeformed shape in the sample लिया है. Yeah. If the same beam is being subjected to some kind of load, like there is a UDL on it, due to this applied loading UDL, the beam will now subject to some deformations. I will just draw some exaggerated scale diagram of the beam which will show its deformation. This is obvious, like more the value of these UDL, the more will be the deformation, or if you keep on increasing the applied loading, the body will undergo more deformation. जितनी ज़्यादा loading होगी उतनी ही ज़्यादा उसमें bending या deformations ज़्यादा होगी. This is obvious thing, common thing. Okay? Just look at the thing now. Okay, this is again the same section 2 inch from bottom. Now when you see this element, it will be now like this one. The element has now been distorted, it has been oriented. ठीक है, इसकी orientation होगी. Originally it was like this one, now it has been changed to this one. ठीक है. So now this element is being shifted to this one, like this one. Now this is the sigma x, here this is the sigma y, and all these stuff. And we may say like that originally this was like this one, now it has been shifted to like 20° or 30° something. The amount of this orientation, 20°, 30, 40, 60, it depends upon how much the body has overall gone under deformations. And this overall deformation of the body, it depends upon applied loading. So more the loading, more the body will deform, and more will be the orientation of this stress element. Just to let you know, like this is the stage 1, the unloaded stage, and this is the stage 2 in which the member is being loaded and deformed. So इस ट्रांसफॉर्मेशन के अंदर बेसिकली अब आपके पास यहाँ जो सिग्मा एक्स है, the sigma x here will no more be equivalent to this one, so we call it like sigma dash, sigma x dash. This is sigma y, we call it sigma y dash. We also have a shear stress value here, maybe like this one, but we call it like tau x y dash. We denote them with a different symbol, like just to distinguish that the value is no more same. Maybe you will have like 8 KSI value some here, and maybe it is 10 now here. Sigma value, maybe it's 10, now it got 12. Tau x value, maybe it It was 15 earlier, now it got 8 now. Just for information, ऐसा नहीं होता कि अगर आपके पास सिग्मा एक्स सिग्मा वाई इंक्रीज कर रहा है तो टॉ एक्स वाई भी इंक्रीज करेगा. They behave in opposite manner. If sigma x sigma y are increasing due to a certain transformation, maybe this transformation can be a clockwise and it can also be anti-clockwise. Okay, so maybe if sigma x sigma y they are increasing, then definitely tau xy will be decreasing. And if tau xy is increasing for a certain transformation, these two values will be decreasing. हम इसको later on बड़ी detail के साथ discuss भी करेंगे and we will perform some numericals because we are interested कि ये जो stress element है while it is rotating, यानी ये rotate करता जा रहा है, अभी second stage या third stage में भी हो सकती है कि instead of a 20 degree angle, now it is being bent like 35 or 40 degree angle. तो अब state of stress थोड़ी सी क्या हो जाएगी, it will be like this one. Now sigma x would be this one. We call it sigma x double dash. This will be now sigma y double dash. Double dash, just to distinguish like this value is no more equivalent to stage 2 and stage 1. Achha. Why we are doing this transformation? Because we are observing here that the values are increasing or decreasing. Okay? They are increasing and decreasing. While designing anything, we design it for the worst case. ठीक है, अगर मुझे कोई चीज़ ये बीम डिज़ाइन करना है तो मैं 15 के लिए डिज़ाइन नहीं करूँगा या 12 के लिए डिज़ाइन नहीं करूँगा. मैं भी मैं चेक करूँगा कि यार इसकी मैक्सिमम वैल्यू क्या है. ठीक है, आई एम इंटरेस्टेड इन दैट पर्टिकुलर ओरिएंटेशन एट दैट पर्टिकुलर एंगल थीटा. ठीक है, एट विच the values of these normal stresses are maximum. So I'm looking for the maximum value of these normal stresses and the maximum values of these shear stresses. Maximum value. So that जब मेरे पास ये values आ जाए, I will use them to find to design my element. The maximum values of these normal stresses, we call them as principal stresses. We will also perform numericals related to these normal stresses. And we call them as sigma 1, sigma 2. Okay, sigma, instead of now sigma x, sigma y, they will be transformed into sigma 1 and sigma 2. So sigma 1 and sigma 2, these are nothing but these are the maximum values of sigma x and sigma y. And this will happen at a particular orientation which we call as theta p. Okay, angle at which principal stresses are occurring. So that this is theta angle. P stands for this is an angle at which principal stresses are occurring. Okay. In a similar way, like you are interested to find the maximum value of shear stress, because I told you, like in the first stage, the value of shear stress is different. In second stage, it may be increasing or decreasing. In third stage, it will further increase or decrease. And at a particular orientation, theta s, we call it theta s, एक ऐसी orientation होगी, theta s, जिसके ऊपर this tau will convert into tau max. So we will design our beam against these values now, principal stresses and shear stresses, instead of looking at these sigma x and sigma y. देखोगे? अच्छा, वापस आते हैं न्यूमेरिकल अपने उस पे शीट पे so this is basically showing the stress transformation. You can even see like previously the values were there may be a possibility in first stage you don't have a normal stress, like sigma y is absent here, but when you do the transformation then you will have a little value of sigma y appearing now. ठीक है, ऐसा भी हो सकता है कि अनलोडेड स्टेज के अंदर सिग्मा वाई जीरो थी और जैसे ही आपने उसको एक खास एंगल के ऊपर रोटेट किया तो बाकी चीजें तो लेट से इंक्रीज और डिक्रीज हो रही थी. ये पहले जीरो थी, इसकी वैल्यू इंक्रीज होके जीरो से अब 10.5 होगी. इनिशियल वैल्यू में इधर जीरो है, देन नाउ इट कम्स 10.5. ठीक है, इसी तरह जिसकी इधर वैल्यू थी दैट वाज 0 as well, and later on it comes to 30.5. ये भी possibility हम देखेंगे आगे. These were the slides जिसके अंदर मैंने बताया था that just a basic revision from MOS1 that I'll show you right now with the big screen. First is the stress strain curve. हम बेसिकली मटेरियल की प्रॉपर्टीज को आइडेंटिफाई करने के लिए कि मटेरियल किस तरह बिहेव करेगा व्हेन इट इज बीइंग लोडेड. So, and what would be the yielding value of load? What will be the failure load? What is the modulus of elasticity? So, to find all these quantities, we usually plot stress strain curve for different materials. Okay? So, इस stress strain curve के अंदर different components होते हैं. That first initially it is a straight line. It is following the Hooke's law, and stress and strain are directly proportional to each other in this region. Later on, you will see there is a yielding phenomena being occurring here. उसमें yielding हो रही है और इस yielding की वजह से ये एक ऐसा point है where the stresses are constant and strains keep on increasing. यानी stress constant रहती है और strain increase करती है. That this stage or this phenomena is known as yielding. Then after yielding, again there is an increase in stresses, and later on there is an ultimate value of stress which we call as ultimate strength. And after that, the phenomenon of necking occurs, and ultimately the material undergo failure or fracture. Okay, so this is the ultimate load, this top one, which this element can bear. So normally we use either this ultimate strength or yield strength for designing members. Like if we have to design a particular member with this material, I will use this value or this value as design strength. So these are two videos. Just look at this first one. अब इस वीडियो के अंदर, इस क्लिप के अंदर कुछ डिफरेंट कॉन्सेप्ट्स को जो है वो एक्सप्लेन किया गया. अब इट स्टार्ट फ्रॉम दिस स्ट्रेट लाइन, स्ट्रेस स्ट्रेन कर्व्स, और दो डिफरेंट मटेरियल्स को भी डिस्कस किया. लाइक सम ऑफ द मटेरियल दे हैव very, what you call it, like a unique points of yielding, जहाँ पे yielding clear नजर आ रही होती है. In the other material, they are like, they don't have a specific yield point. तो मैं एग्जांपल वैसे देता हूँ, लाइक कंक्रीट अगर आप देखें, कंक्रीट का स्ट्रेस स्ट्रेन कर्व देखें, सो यू विल नॉट फाइंड दिस यील्डिंग फिनोमेना देयर. ठीक है, मैं इसको ड्रॉ करता हूँ ऑन दिस स्क्रीन, मे बी ऑन दिस वन. लाइक इफ यू, this is the stress or strain, maybe this is strain going down. Because strain is always on x-axis, then the stresses are here. So there may be a possibility that if this is for a concrete material, it would be like this one. Okay. Similarly, if this stress strain curve is being drawn for steel, so now this looks like this one, increase and decrease. This. See, this is a point where you can see the value of stress is being constant, but strain is increasing. Here the strain is this one, here the strain is like 4 or something. So strain is increasing in this region, but the stress is constant. So it is yielding phenomena going on here. Okay? But in the above case, which is a concrete or brittle material, this is bottom is steel, which is a ductile material. So इसके अंदर जो है वो आपके पास yielding phenomena काफी quite visible था. इसमें visible नहीं था, so you use a 0.2% offset method, the one discussed in the video clip. Secondly, the important thing he discussed, like we have different strength criteria. One is called the yield strength criteria. Okay? We call it like Fy, and then there's another one which we call is FCU, like ultimate tensile strength. This is the ultimate tensile strength, and this is the yield strength. So sometimes we want the material not to be not to undergo plastic deformation, because once this elastic deformation region is finished, then you enter a plastic deformation state in which the body's deformations are irrecoverable. Means कि अगर आप बॉडी को अनलोड करेंगे तो बॉडी अपनी ओरिजिनल शेप गेन नहीं कर पाएगी. ठीक है, some of the materials are like this one. When you load them, they undergo deformations. When you unload them, they come back to their original shape and original everything. ठीक है, उस अपनी शेप को रीगेन कर लेते हैं. This is happening in this stage when you are applying the loading under this yielding stage. यील्डिंग के बाद उसके अंदर परमानेंट डिफॉर्मेशन आना स्टार्ट हो जाती है. तो उसके बारे में भी डिस्कशन हुई. Then important parameter was discussed about ductility, material toughness, material resilience. तो ये important properties हैं which are part of your exam. आप उसके अंदर से क्वेश्चंस पूछा जा सकता है. What is the difference between material toughness and material resilience? They both look same, like you have to calculate the area under the stress strain curve, but the major difference is like the total area under the stress strain curve. This will give you the value of material toughness. And however, on the other side, if you just sum up the area under the stress strain curve before the yielding point, yielding से पहले पहले तक के region को करेंगे, यानी ये आपके पास यहाँ तक का जो region है इसको करेंगे, this will give you resilience. But instead of this one, if you consider the whole thing, like from here to here and here, this total area को sum up करेंगे, then you will get material toughness. Then he mentioned like the material toughness is basically the amount of energy a material can absorb before failure. This is an important criteria while designing members. We want them to be ductile. ठीक है, हम नहीं चाहते कि हमारे structure brittle हो, because once you are designing any kind of structure, maybe it's a building, a bridge, or a wall, or cantilever column, anything, any kind of structure, if this structure is to be designed and constructed in a region where there are seismic forces, where there is a high possibility of seismic activities, so it means that whenever this activity is occurring, like जैसे ही ज़लज़ला आता है, earthquake activity आती है, so this the seismic wave, they introduce energy into the building. ठीक है, वो waves जो आती हैं, they are carrying energy. So these energies, the waves which are carrying, they transform these energy to the building structure or any structure, वो उसके अंदर enter कर देती हैं उसको. So now the structure needs to dissipate this energy. How the structure dissipate this energy? It moves to and fro. ठीक है, वो sway करता है. And while it's moving to and fro, it is basically dissipating that amount of energy which is being introduced through the earthquake waves. ठीक हो गया? So you need to have a ductile material so that it can dissipate the big amount of energy which is being introduced into it. ठीक है? There are two ways in which the energy is being dissipated from structure. One, I told you, like it moves to and fro. ठीक है, बॉडी आपको या बिल्डिंग्स आपको sway करती नजर आएंगी. This is a common phenomena you see in Japan and you see in United States, that the buildings are swaying under seismic loads and even under wind loads. But that sway is not disturbing you. वो इतना ज़्यादा at once नहीं होता, हल्का हल्का building sway कर रही होती है constantly, and it is dissipating that energy. The other thing, like you would know कि building energy dissipate कर रही है. This is the formation of cracks. Whenever you see cracks in a building, ठीक है, उसकी shear wall के अंदर cracks develop होंगे. This is an indication like the building is dissipating energy. ठीक है, energy को निकाल रही है. कौन सी energy को निकाल रही है? Which is being introduced into it through earthquakes. So you need to have ductile materials. Otherwise, वो स्ट्रक्चर जो होगा वो फेलियर की तरफ आ जाए, बिकॉज यू डोंट वांट टू हैव क्रैक्स इन योर बिल्डिंग. इंस्टेड यू वुड प्रेफर कि बिल्डिंग हल्का सा सोए करे विद इन लिमिट्स एंड डिसिपेट करे उस एनर्जी को. सो it's preferable to have materials with high toughness instead of using material with low toughness. Now coming towards annotate was gone. Oops. Okay. Now coming toward the second point, the second clip, which is for Poisson ratio. इसको मैं भी यहाँ स्टार्ट ही करूँ बिकॉज दिस इज 1 मिनट, हमारे पास 2 मिनट रह गए इस सेशन को क्लोज होने में. मैं सेशन दोबारा स्टार्ट करूँगा. आई शेयर द लिंक, तो आप उसको ज्वाइन कर लें. आपके ग्रुप के अंदर ही शेयर करूँगा. आई जस्ट टेल यू कि पॉइजन रेशो आपने वैसे भी स्टडी किया होगा फिजिक्स के अंदर, कि बॉडी के अंदर दो डिफरेंट किस्म की स्ट्रेन होती हैं. वन वी कॉल एज लेटरल स्ट्रेन एंड वन इज कॉल्ड द लॉन्गिट्यूडनल स्ट्रेन. This has been shown in this figure as well. If you have a closer look, तो जैसे आप इस स्ट्रिप को दोनों तरफ से मूव करें, सो यू हैव दिस लॉन्गिट्यूडनल स्ट्रेन, यानी जिस डायरेक्शन के अंदर आपने फोर्स अप्लाई की हुई थी उस डायरेक्शन के अंदर जो स्ट्रेन्स प्रोड्यूस होती हैं, दे कॉल्ड एज लॉन्गिट्यूडनल स्ट्रेन. एंड द स्ट्रेन्स व्हिच आर produced in the direction perpendicular to the direction of applied load. See, applied load is along x-axis, where these strains, okay, uski thickness reduce हो रही है. These are called the lateral strain. So the ratio of this lateral strain over longitudinal strain, this is known as Poisson ratio, and this is constant for some materials. ठीक है जी. हम इससे रिलेटेड पॉइजन रेशियो से रिलेटेड इस कॉन्सेप्ट को अंडरस्टैंड करने के लिए एक छोटा सा क्लिप है, इसको देखेंगे. Okay, this is the second video, but we will just go through it now. It's related to Poisson ratio. Let's have a look on this one. ठीक हो गया जी। तो ये डिफरेंट वैल्यूज हैं डिफरेंट मटेरियल्स के लिए फॉर द पॉइजन रेशियो लाइक फॉर कंक्रीट इट इज 0.1 to 0.2 फॉर रबर इट हैज अ डिफरेंट वैल्यू so the more the value of Poisson ratio it means when you applied a load on that material it will undergo higher values of literal strain जितनी उसकी ज़्यादा वैल्यू है Poisson ratio की उतनी ही उसमें literal strains जो है वो ज़्यादा होंगी this is the definition यहाँ पर bottom पे भी लिखे this is the ratio of lateral strains to longitudinal strain I believe कि अब आपको lateral और longitudinal का concept clear होगा longitudinal strains या longitudinal direction basically वो direction है in which the forces are applied maybe the forces are applied in y direction or maybe the forces are applied in x direction जिस direction में भी force apply हो रही हो that will be the longitudinal direction and the strains or the quantities which are perpendicular to the direction of applied loading these are considered as lateral strains or lateral ठीक है जी अच्छा जी in this slide there is a phenomena of necking which is being shown here like when you are applying a force on this member like a tensile load so as a result of this tensile loads definitely the length of this member will increase like this is the first stage in the second stage you will observe that the length has now been increased from this much to this much on the other side there are longitudinal strains going on here because the force is in this direction unlike in the previous example where the force was in this perpendicular x-axis direction, now it's in y direction because let's say it's a column something or maybe it's a cylinder something which is being tested. So now this is the longitudinal direction. Is it clear to everyone? Like this is the longitudinal direction now. ठीक हो गया जी? And once you apply the force now, previously the length was like this one. In the second stage, the length has now been increased. So there are longitudinal strains. This is now longitudinal direction. So longitudinal strains are there. At the same time, the thickness or the diameter of this element has now been reduced. So this thing is now transverse direction because this is perpendicular to the direction of applied loading. So now there are lateral strain as well. So if you keep on increasing the load, you will see that this thickness or this diameter of this specimen, it will keep on decreasing, decreasing, and you will see like it becomes like this one. This is called the necking. Like this, originally it was like this one, and at the point of maximum stress, it's coming like this one. This is called the necking phenomena here, and ultimately the failure will occur at this point. Okay. An important thing which I will tell you here, like once you draw the stress strain curve like this one, okay. So some people they say like uh, like why there is an increase in stress like once the yielding has been occur. So after the yielding, you can see that the stress is again increasing. Okay. So stress क्यों increase करती है? Because there is a necking phenomena going on in the materials. नेकिंग फिनोमेना के अंदर अगर आप देखें तो एरिया जो है बेसिकली इट इज रिड्यूसिंग ठीक है हमारे पास फॉर्मूला होता है स्ट्रेस इज इक्वल टू फोर्स पर यूनिट एरिया ठीक है so area and stress they are inversely proportional to each other if the stress if the area cross sectional area of the material is decreasing then it means stress will increase so once you cross the yielding point ठीक है जैसे yielding खत्म हुई तो बॉडी के अंदर नेकिंग का फिनोमेना स्टार्ट होता है एंड द क्रॉस सेक्शनल एरिया इट स्टार्ट डिक्रीजिंग एज द रिजल्ट ऑफ डिक्रीजिंग दिस एरिया द स्ट्रेस विल इंक्रीज सो नाउ देयर इज अ शिफ्ट कि जब यील्डिंग खत्म हुई तो उसके बाद देयर इज एन इंक्रीज इन स्ट्रेस व्हिच इज कॉल्ड नेकिंग ठीक है जी ये कुछ वीडियोस के अंदर अगर आप स्ट्रेस स्ट्रेन की देखेंगे तो उसमें बड़ा क्लियर विजिबल होगा ये फिनोमेना नेकिंग का फिनोमेना और वो अगर मैं थोड़ा सा इधर बल्कि क्लियर ड्रॉ करता हूँ लेट मी ट्राई कि यहाँ पर इस तरह करते हैं इसको जूम तो नहीं हो रहा ये तो आपको वहाँ पर जो नज़र आएगा ना वो इस तरह करने के इस तरह नहीं होगा बेसिकली वो थोड़ा सा इस तरह एब्रप्ट आके ऊपर से यूँ नीचे आता है ठीक है एंड देन इट गोज लाइक दिस वन सो दिस इज बेसिकली the necking phenomena going on, कि एकदम abrupt stress के अंदर change increase आता है and then yielding occurs इस तरह. ठीक है, तो हम करेंगे. Now coming towards the combined stress thing, कि what is a combined stress और हम किस तरह इसके न्यूमेरिकल्स को देखेंगे. फर्स्ट यू नीड टू नो कि ये स्ट्रेस एलिमेंट है, द वन ऑन योर फिगर, this one we call them as sigma x normal stresses, we call them sigma y. Why we call them as normal stresses? Because this is the face of the element. You can see this is the face, and on this face there are three stresses which are being shown. One this one, this is the second, and this is the third one. Okay, so the other two, these two, both of them, they are parallel to the this face. And things which are parallel, they are called shear stresses. हमने जिस तरह देखा था कि if there is a beam, you cut a section here. Once you cut a section, there are normal forces, there are shear forces, and there are moments. So for these shear forces, because this is parallel to this section, so this shear force will develop shear stresses. Similarly, this normal force is perpendicular to the section, that why it develops normal stresses. In the same way, these are normal stresses, these are the shear stresses. They have a different notation here, like sigma x is very obvious, sigma y is very obvious because it's going on in y direction, that's why you call it sigma y, you call it sigma x. Now coming towards how you will denote these tau xy and tau xz. Okay, there are two subscripts, like the first and second. The first subscript is basically showing like on which plane these stresses are occurring. Okay, यानी ये stresses, shear stress, this one and this one, ये किस plane में occur कर रही हैं. So if you want to know the name of a plane, जिस तरह ये cube बना है, so the cube has 6 planes, 6 surfaces. ठीक है, this is the surface, this surface. ठीक है, जिस तरह हम ये छोटा सा cube draw करते हैं, like a tricky thing, जब हम छोटे होते तो इसमें दो क्यूब्स को कंबाइन करते थे, we make it a 3D one. So now you can see that it has different surfaces. ठीक है, so each surface has a name. How you can identify the name of the surface? You just need to see what axis is passing through it. For example, if I am looking at this red one, इस face को देख रहा हूँ, so I will see what axis is passing through it. So x axis is passing through this face, so I'll call it like x face. So the first subscript will be x. If you look at this this one, like this, if I'm talking about this surface, this face, so I will see like which axis is passing perpendicularly through this face. It is y. It is very common. X axis is parallel to this one. Z axis is also parallel to this one, but y axis is perpendicular to this face. So we call this face as y face. So first subscript will be the face on which these stresses are occurring. The second subscript will tell you like this shear stress is in x direction, y direction, or z direction. So it is very obvious, like the arrow is going on in y direction. So we name it as tau xy. Similarly, tau x, it is going in z direction. That's why we tau xy. So let's start again. So we have this sign convention. इस next slide के अंदर basically इन elements को भी आप देखिए explain किया हुआ है. ठीक है जी. So in reality, the stress, this is basically the stress element. If I tell you this is a stress element, because in reality the bodies are in 3 dimension. Now you need to understand this thing ताकि चीजें confuse ना हो. In real thing is the bodies are in 3D. ठीक है, आप जो भी body देखते हैं, beam देखते हैं, if you see a beam, a column, or a structure, even everything, if you see it at a global level, it is a big structure, a bridge, or maybe a building. And if you see at a local level, it will be a beam, structural element, maybe it's a column. So in each of these structural members, beam and column, if you go through in detail and check the stress element, so because the body is in 3D, so the stress element will be also a 3D element. ठीक है, but for simplification we draw it as a 2D element. ठीक है, हम अपनी simplification के लिए आगे जाके मैं आपको explain करूंगा that this 3-dimensional stress element is now being changed into a 2D element just for simplification, because we want to solve the structure. हम structure को analyze करना चाहते हैं, that's why we have to make some simplification और हम assumptions करते हैं. So the assumption is like, we consider sigma z equal to 0. Again, all the numericals that you will do here, you will consider sigma z is equal to 0, and we call these numerical as plane stress numerical. So once you are being asked like what is plane stress numerical, or what is the concept of plane stress, so plane stress problems are the problems in which sigma z, or the stresses in z directions, they are assumed to be 0. So you will have only sigma x and sigma y. ठीक है, अगर इसी चीज के अंदर मैं सिग्मा z को खत्म कर दूंगा, तो ultimately you will have a block here which has sigma x, which has sigma y. So these are called plane stress numericals. One important thing you must also know, that this tau xy and this tau yx, I will later prove on, like the values of these two shear stresses which are occurring on these faces, simultaneous faces के ऊपर occur करिए, these values are same, यानी tau yx will be equals to tau xy. ये दोनों आपस में equal होंगी, but they have a different sign. Like the head is always connecting to a head. If there's a tail here, the tail will be going there. So head will be connecting to head, or tail will be connecting to tail. अच्छा जी, आगे चलते हैं जी. Combined axial and bending stresses. So I already explained you, like maybe the body is subjecting to such kind of loading that it will develop the axial stresses. This is the axial stresses, P over A or N over A, whatever you call it, you maybe call it as F over A something. So this is the axial stress, plus this is the bending flexural stress. So the formulas we already have discussed while detailing the individual stresses cases. Plus minus के sign उनके साथ है, which you have to select either it is a plus, either it is negative. Similarly for this one, you need to select either it is a positive or negative thing. These are some examples, like when the bodies are being subjected to combined state of stress, like this is a bridge wall which is having a dead weight. See, सही है, तो इसकी एक side के ऊपर water है, on the other side you have counter force retaining walls. ये आपके पास counter force पड़े, so they are trying to resist the applied action of this water. This weight of the dam wall, it is acting downward. So there is a load in this direction, there is a load going on this direction towards a left side. There is a water which is trying to push this boundary or this wall in right direction. So simultaneously this wall element is being subjected to different kind of loading. As a result, there will be not a single state of stress inside it. Instead, there will be different kind of stresses, and you have to find the combined state of stress in order to design this wall. ठीक हो गई? तो different elements के against उसने ये show किया हुआ है. अच्छा जी. The figure 1 is basically showing the stress distribution diagram, like if the body is being subjected to axial or normal stresses. So you cut a section here, you will see that the stress distribution is like this one. Similarly, if the body is being subjected to bending loads, moments, you apply the moments. These are the action forces. By the way, in last lecture, कल के lecture में मैंने काफी detail के साथ explain किया that the first thing is that you need to identify what kind of individual stresses. Once you are finding the combined stress, तो combined stress find करने से पहले आपको ये पता होना जरूरी है कि कौन से individual state of stresses exist कर रही हैं. Second, आपको ये पता होना चाहिए कि उनके signs क्या हैं. Once you know these two things, you can able to find the combined stress. तो आपको किस तरह पता चलेगा कि कौन सी state of stress या what different kind of stresses are occurring? This will be identified with the applied loading. कि applied loading की nature क्या है? See, in this first case, the applied loading is axial force P or normal force. So this normal force is obviously producing axial or normal stresses. Similarly, if this applied loading is a moment, so definitely it will produce flexural stresses or bending stresses, which is being shown here. So this is the flexural stress distribution diagram, which we have discussed in yesterday's lecture. That On top fiber, you will have extreme values, and once you move towards the neutral axis, this is the neutral axis. I'll just denote it here. So this is the neutral axis going on here. And once this moment is occurring, so the body will undergo deformations like this one. This is just an exaggerated scale diagram. And due to this applied loading, this is the deformation diagram. So you will have a compression on top and tension at the bottom. So these extreme points, they will have a maximum compression. The compression will start decreasing, decreasing, decreasing. Ultimately, once you reach at the neutral axis, the compressive stresses, okay, those stresses will become zero. ये जो डायग्राम यहाँ पर शो हुई है, दिस इज स्ट्रेस डिस्ट्रीब्यूशन डायग्राम. दिस इज नॉट द नॉर्मल फोर्स डायग्राम. ठीक है, एक होती है नॉर्मल फोर्स. जब आप सेक्शन कट करते हैं तो मैं आपको कहता था नॉर्मल फोर्स है यहाँ पर. ठीक है, सेक्शन कट करने के बाद यहाँ एक नॉर्मल फोर्स है, देन देयर इज अ शियर फोर्स एंड देयर इज अ मोमेंट. ये इनकी वेरिएशन नहीं है, इनकी तीनों की इंटरनल फोर्सेस की जो वेरिएशन होती थी, दैट वी कॉल एज एसएफटी, बीएमडी, शियर फोर्स डायग्राम, बीएमडी डायग्राम. Those diagrams are basically showing the variation of these internal forces. These are internal forces. These are stress distribution diagram, not forces. ठीक है. Similarly, वो बता रहा है, कहता है कि in case if the body is being subjected simultaneously with these two cases, case 1 and 2 simultaneously, if you load them, so this will be the case. And now this, you have to add these two things. So this is the combined state of stress. उसकी वजह से जो stress distribution आएगी, you have to add them, these two cases, and this will result in this thing. ठीक हो गया. Okay, plane stress and strain conditions. I explained like this is the 3D problem, because the elements we are going to analyze, a beam, a column, or something, these are always a 3D elements. And once you extrude a sample or a stress element from them, that element should be a 3D as well. So for simplification and for solving things, we considered that this is no more a 3D problem, this is a 2D problem. And how we can achieve this, we will consider like sigma z is 0. Similarly, all the shear stresses which are on z face, see, they will be considered as 0. यहाँ पर sigma z को भी 0 करेंगे, tau xz, tau yz. These shear stresses, they are occurring on this faces. ठीक है, इनको आपने 0 consider करना है, and then the out of these 6 components, 3 will lost, and you will get only 3 components. ऐसे ही है sigma x, sigma y, and tau xy. Clear? Previously you have a 6 component, and out of those 6 components you have deleted these 3 components, considering like the stresses in z direction, they are 0. So now this 3D cube will convert into this 2D problem like this one. Okay, and when you orient this one, so you have like this stress element. जिसको हम आगे solve करेंगे. अच्छा जी, just let me know. This is another clip for just to showing कि what is plane stress and strain conditions. इसको भी देखिएगा. This is important now. Let me just try to play it. अच्छा जी, आई होप सो दिस इज वेरी अंडरस्टैंडेबल कि हमने देखा है कि डेफिनेशन पहले प्लेन स्ट्रेस प्रॉब्लम्स की क्या है और व्हाट इज़ अ प्लेन स्ट्रेस कंडीशन क्या चीज़ है, एंड यू नीड टू हैव सम make some assumptions. हम ये assumptions क्यों करते हैं? Because we need simplifications in order to solve the problems. Numerical problems जो कि 3D world problems होते हैं उनको हम solve करते हैं, but you need to make assumptions, and these assumptions they come with engineering judgment. You need to make sure कि अगर आप उसके अंदर third dimension के stresses को zero करें, so this will not affect the outcomes of your results. ठीक है जी, तो उसको वो compromise ना करिए. अच्छा जी, this is a normal beam आपके पास show किए, and there are some stress elements being shown at different locations. Stress element 1, 2, 3, 4. So the obvious thing here is what I will explain now, using this. Just a minute. जब हम numericals कर रहे थे, so we discussed like there is a flexural stress distribution diagram like this one. If I draw it like this one, it would be this one. And for a simply supported beam, if you look at the shear stress distribution diagram, the shear stress distribution diagram was like this one. Okay, so this is for shear, this is for flexural stresses. So you can see that the flexural stresses, they are maximum at these points. These are the maximum values. Similarly, if you're looking at the shear stresses, so these shear stresses are maximum at neutral axis. Shear stresses, they are maximum neutral axis. Flexural stresses, they are zero at neutral axis. On the other hand, if you just look at what are the maximum values, so these are the maximum points, and for the shear stress, this is the maximum point. Here it is zero. It is zero here. So the same thing which we have discussed in this form is now being shown here. Like if the element stress element is being located on the top outermost fibers, maybe the top fiber or the bottom fiber, so there are no shear stresses here. You see, there is no shear stress here, there is no shear stress here. Only the arrows are showing the normal stress. Okay? Again, for fourth location, because it is locating on the outermost fibers, so shear stresses will be zero. See, distribution is also showing the same thing. Secondly, once you come at the neutral axis, so once that you are neutral axis, so you know that the flexural stresses will be zero at neutral axis. That's why you don't see arrows here like sigma x and sigma y. They are no more here. But you will see the shear stress. These are for the shear stress. All these four arrows, they are for shear stress. So if your element is located on the neutral axis, so you will have no flexural stresses or normal stresses. Instead, there will be only shear stresses, pure shear stress case. This is a pure normal stress case. This is a pure shear stress case. In between there, if there is any other location, maybe it's this one location, maybe any this location, any location in between them, so you will have this concept applied here. Like you will have some value of normal stress, you will have some value of shear stress. ठीक हो गया जी? अच्छा जी, इसको हम करते हैं make it clear and we just move on now. Mark. अच्छा, इसको रहने दें जी, ये भी हम डिस्कस कर चुके हैं. We already have discussed these things. पॉजिटिव साइन, नेगेटिव साइन भी हम डिस्कस कर चुके हैं. Okay, plane stresses के अंदर further we have a uniaxial stress system. Like you don't have even sigma z to high zero because this is a plane stress problem. So even in a plane stress problem, if you have only sigma x or only sigma y, then it is called a uniaxial. Uniaxial means single direction stress. So if there is only sigma x or even sigma y only, like sigma y has sigma x नहीं है या sigma x or sigma y नहीं है, then these problems are called uniaxial stress systems. If they have two different like sigma x and sigma y, then it is called a biaxial. Bi means two, biaxial stress. The third is showing basically the pure shear stress, like there are no normal stresses occurring here, so this is called the pure shear stress problem. This pure shear stress is basically occurring, if you see here in the diagram, it is occurring here on the neutral axis where the flexural stresses are zero. ठीक होगा जी? Okay, now we will do some derivation, जिसके अंदर हम देखेंगे कि नॉर्मली जब आपके पास अभी तक जितनी हमने डिस्कशंस की उसके अंदर मैं यही कहता था कि लाइक दिस इज अ बीम and you have to like cut a section here like this one. Once you cut a section here, the body will be like this one, and you will have a different value of a normal force, you will have a value of a shear force, you have the value of moments. These are the three internal forces that will be developed in the body when you cut a section here. So in most of the cases what we have discussed until now, I was making this section perpendicular to the body. Like this is the body, this is the longitudinal axis, like this one. So I'm making this section perpendicular to the longitudinal direction, isn't it? Now we will look at the things like if we cut this section instead of like this one, if we make an inclined section and then see like what's the body is having, like the body will be now looking like this one. So now what will be the state of stress? What will be the stresses here, and how we are going to relate these stresses with this condition? Like this is the stage 1 or this is the state 2. So once there's an inclined section, you will see like there are stresses here like this one, or in the previous case like if you see this again here like this one. So once the section is being cut, you will see like normal stresses are here. Again, when the section is inclined, now there are again stresses here, but these stresses are no more perpendicular. See, this is a line and this is, I'm drawing these arrows. Instead of multiple arrows, I'm just drawing one just to elaborate the concept. So अब यहाँ पर this is no more perpendicular. Previously, when once you are in this case, like this was this one and there was an arrow here, so this was perpendicular to this section, but now it is no more perpendicular. So what will be the state of stress here and how you are going to relate these stresses with this case? We will look at this problem through a derivation. So this is we call as a normal section and this we call as an inclined section. Okay. You can see here as well, like if the body is being subjected to axial or normal forces, like it is being subjected here to a tension load, okay, axial force like here, and you get a normal section, okay. So once you got a section, you will see here that the stress distribution is like this one, like this force is being resisted by these arrows, and this is sigma, which is equal to P over A, okay. The value of these applied forces, maybe it's P or F, whatever. So you have to divide this applied force with this cross sectional area, then you get the axial or normal stresses, which are being showed by the uniform distribution of these arrows. Okay. Now in the second case, you will again have the same column, the same loading, but now the section is oblique or maybe it's an inclined. So there will be stresses here, normal and shear stress. So you have to correlate these two cases with each other. Why we are looking at this inclined section? Because I told you that while the body is being subjected to applied loading, it will deform, and once the body is deforming, जब body deform हो रही है, bend हो रही है, तो bend होते हुए उसके अंदर जो element हैं, they are undergoing orientation, उनके अंदर stress transformation हो रही है. So you need to check like when the section is straight and when the section is inclined, the stresses are increasing or decreasing, normal stress is increasing or it is decreasing, or shear stress is increasing or decreasing. इस चीज को आपस में देखेंगे. ठीक हो गया जी. सेकेंड, इस इंक्लाइंड स्ट्रेसेस के ऊपर, इंक्लाइंड प्लेन के ऊपर स्ट्रेसेस निकालने का एक और फंक्शन भी उसने यहाँ पर एप्लीकेशन दी. लाइक you have a body which is being welded like this body is composed of two different materials, and these two materials are connected with a weld here. The weld is inclined. So when you applied the load on this member, the obvious thing is like it will not fail here, it will not fail here. आपके ज़हन में ये आएगा कि यार weld is a point, या weld is the plane जहाँ पर possibility है कि यहाँ से failure होगा इसका. So you would like to analyze this beam at this inclined plane. इस plane के ऊपर ला के रखना चाहेंगे. That is why you will place your stress element, ठीक है, not like previously हम क्या करते थे, अपने stress element को यूं plane करते थे, but now because we want to analyze the state of stress along this plane, inclined plane, so that's why you cannot use this one. You need to orient your stress element like this one, ठीक है जी, इसलिए हम इस चीज को एनालाइज करना चाह रहे हैं.